Welcome back, Math 170. We're going to look at section 1.6, using the limit laws. A lot of you might enjoy this. There's a lot of mechanics here in terms of a lot of algebra going on. I encourage you, a lot of these limit laws and properties are intuitive. They kind of work how you think they would work. So we're not going to spend too much time reviewing them. We're going to look at applying them. So I encourage you to go through your textbook or even kind of go over these properties I have listed down and make sure you're understanding them. And then just let us know if you have any questions. So we'll start off with the direct substitution property. And this is something that you might have already figured out already as we were looking at section 1.5. But if we can, they're trying to tell us if F is a nice, and usually when we talk about nice in our class, they probably mean a little bit more in terms of smooth. We want to think of the functions in the toolkit. So if you end up having one of these nice functions and there's actually a value that exists when you plug in x equals a, and you actually have a value that exists, then you can say that the limit of f of x as x approaches a is equal to that value. So in other words, you're really just plugging in that particular a value into your function. So if we kind of do a few, just so that you can see, we have our limit of x squared as x approaches 5. If you think about what it looks like to be y equals x squared, that's a very nice function, nice parabola. It's smooth. We also know in a parabola that our f of 5 exists. And let's see if I can write that a little nicer. Just a reminder, we have f of x equals y equals x squared. If that is the case, then when we want to calculate the limit of x squared, we could simply take that particular a value and we're going to plug it into the function. So that's 5 squared. And so the limit is going to be equal to 25. Now, same story, some of our popular functions, if we ended up having f of x equals or y equals x, that's also a nice, smooth, linear function. We do know that f of 5 exists there. So if that is the case, we can take that 5, plug it directly into our function itself, which is all we have to do is write the 5, and we do have our limit. And so we'll see, part C, you get a little bit more complication. What if we have the sum of the two functions? A little bit of a limit property. There's two ways to think about it. The first way, when we're talking about the direct substitution property, the function that we see, x squared plus x, that's a polynomial. It's nice, it's smooth. And usually in polynomials, there's no holes or gaps. F of 5 does exist. So you can use direct substitution and plug the 5 into the formula. So we would have 5 squared plus 5, or 25 plus 5, equals 30. So we have the limit of that function. Alternatively, you might want to notice that you have a sum of two functions in the argument. So one could have thought about it as rewriting this limit as a sum of two limits. Limit as x approaches 5 of x squared plus limit as x approaches 5 of x. And if you see, we already did this in part A and part B. We got 25 for the limit of x squared as x approaches 5. And we got 5 for part B. And you also see that that is equal to 30. So a couple ways to approach it. Usually when you see polynomials, direct substitution is the way to go, but the reason why it does work is because we do have these nice properties, particularly property number 1, property number 2, and property number 3. So just kind of keep that in mind. It's a little bit of computation for you. I want to now look at this, a little analytic geometry here. Let's suppose we don't know the equations of the two functions. We have f and g given to us, and it looks like we have, there's some smoothness, there's some jumps here and there. So what we want to do is we want to calculate the limits, and here we're going to have to use function notation and understanding how this works with viewing x values and corresponding y values. So what I'd like to look at, it appears if I'm looking at part A, what I have is the limit of a product. And that is property number 4 if we're looking on the first page. And if you want to rewrite it to help you see this a little bit better, the functions themselves are not smooth, they're separate, we're not sure what we're supposed to be looking at. I prefer to rewrite it as a product of two separate limits. We're looking as x approaches -1 of f of x, multiplying it by the limit as x approaches -1 as well of g of x. So this allows us to look at the two separate graphs to see if we have, we were able to find some values for these. So what I'd like to pay attention to is what's actually happening around x equals -1. So I'll write it in. Sometimes I like to label it so I can see. So we'll write this in red, and -1 according to where these pictures are, we have right here. We always have to look at where the origin's located in some of these web assign problems. Sometimes it's not in the center like we think it is, so just kind of be careful. So I'm marking where x equals -1 so I can understand this a little bit better. And I want to figure out, as x approaches -1, what are the y values doing when we're on the f of x function? So I'm going to look at this in terms of, I'll look at a green. And so remember, we're starting off by looking at what happens from the left side. If you're looking at x values, it appears that the y values are approaching +1. So that's coming from the left, a one-sided limit. If you're also looking from the right-hand side, looking at the corresponding y values, in all cases, it seems like they're all going to be approaching +1. So remember, something that we kind of played with, we'll state this a little bit more explicitly, but we can say if the two-sided, one-sided limit is equal to the other side limit, then the limit of the entire function is the same number. So I can say from understanding the way the graph is behaving, around x equals -1, it appears that those corresponding y values are always approaching +1. So the limit is +1. Keep in mind that's going to be multiplied with whatever I understand with the g of x. And with the g of x, I'll use purple. Again, we're approaching -1 from the left side, one-sided limit. If we're looking at that, it appears that the y values are approaching this part right here. It should be 2 if we're going to label it. I would label it on the left of it, but I want to use that for drawing purposes. So from the left side, the function, the x values, as they approach -1, the y values are approaching, they're rising to 2. And if we go on the right-hand side, values of x that approach -1 from the positive side, it appears that all their y values are also approaching 2. They're dropping to 2. They're getting smaller and smaller until they hit 2. So that would be the limit of our actual function. From the left-hand side to the right-hand side makes that +2. Now, if we're going to find the limit of the product of these two, using the property number 4, we're multiplying this out, and we will get 1 times 2 equals 2. So a little composition there. Now we can do the same thing with part B. I might need a little bit more space here. See if I can label this, and then we'll get there. So with part B, I'll write this on the side so we can see. I would prefer, I think that's property number 2. It looks like we have a subtraction in between the two functions. So what we're looking at is we are going to rewrite this. I always recommend this because it helps us interpret. We're taking the limit of f of x as x approaches 0, and we'd be subtracting off the limit of g of x as x approaches 0. So then that breaks the problem down into 2 nicer problems for us to inspect. I'm going to go back to the graph. I'm going to erase my markings from the previous problem because we might not need them. And if we look at this carefully, we kind of see that, well, what x value are we looking at? We're going to mark where 0 is. And it's already marked for us, but I like to remind myself what that's looking like. So the limit of f of x, that is the graph on the left. We are trying to determine what's happening to the y values as the x values are getting close to x equals 0. So on the left-hand side, it appears that the y values are approaching 2. On the right-hand side, it also appears that the y values are approaching 2 for every corresponding x value. So we can say that limit is equal to 2. Remember, we're using subtraction. For the g of x function, we're going to look at the graph on the right, and we are looking at what's happening as x approaches 0. So maybe to the side, if we can see this, I'm going to use, if we're looking at coming from the left-hand side. So all of the corresponding x values with the y values, it looks like they're rising, and it appears that they, and maybe I'll write this up on the side, the limit as x approaches 0 from the negative side of your, it's g of x. Here we go. It appears that they are approaching the value of 3. So I'll look at that. But now if I look at this the other way, coming from the right-hand side, if I take the limit as x approaches 0 from the positive side of the same function, the corresponding y values appear to be dropping to 1. And so if you remember, we spoke a little bit about section 1.5. This is not a match. So if the function value, the limits are different, then we would have to say the limit of g of x as x approaches 0 does not exist. So what that would look like in your part B is we would have a D and E coming there. And whenever you run into a case where, part of the expression, works, you have a 2, and anytime you have an issue with one of the expressions where they do not exist, that means, you can't subtract a do not exist from a 2. So you would say, finally, the limit of that expression, part B, in general, does not exist. So anytime a D and E shows up, I just say, everything doesn't work. So be careful there. Sometimes it's tricky with that limit of f of x as actually having a number, but keep that in mind. So with property C, I just want to kind of point you, or part C, sometimes they're not asking you to look at limits of everything. Sometimes they want you to look at the function notation itself. So if we were looking at f of -1, there's no limit involved. So let me erase some markings on the previous part. And let's just look at the function on the left. That's the f. And all they want us to do is find the y value. When x is -1, what is the y value? And when you look at the function, we're not looking at limits, we're actually looking at the corresponding y value. It happens to be 3. You see that little point up there? Interesting. So that's the number 3. There was a plus sign from the expression. Now we're going to look at what is the limit of g of x. That's the right-hand side as x approaches -1. And I believe we already did this. But you can see in both cases, the y values are actually approaching +2. So the value of part C, we just add the 3 and the 2 and we get a 5. So not everything always has to do with a limit, so just kind of keep that in mind. They tend to throw some of those in there so you remember function notation as well. So that's a little bit of looking at the graphs to determine the limits. Now I have a little slightly more interesting problem. We can inspect the graph on this if we want to. Might be kind of beneficial at this point, but it is slightly more interesting. I would kind of point out if you were trying to use direct substitution, because that's usually everyone's first thought. Why can't I do that? Look at what happens when you plug in x equals 3 to the denominator. So if you plug in x equals 3 to the denominator, 3 minus 3 becomes 0, and you get a function that's not defined at x equals 3. Whenever you have a denominator of 0, then we said that that's undefined, so be careful. So if that is the case, we need to make sure that we do not try to plug in x equals 3 to the entire function. But there is kind of an interesting part about this. We don't really care about x equals 3. That's kind of the thing we have to be careful about when we're looking at limits. We care what happens near 3. So that's kind of a good news to us. So if we play along, sometimes there's some algebra from your past that you can use to help with getting rid of some denominators that might end up being undefined for certain values. So let's play. I'm going to take the limit as x approaches 3 of x squared minus 9 over x minus 3. That's kind of our original problem. And some of you might notice, I'm going to move horizontally. Sometimes that's nice because I can do my explanation here. You might be noticing the numerator. You might be saying, I remember that. That's a difference of squares from my past. So, you know, normally that's kind of the natural thing to do is let's see if we can factor that. So if I look at the limit as x approaches 3 and I look at my new factorization, I have x plus 3, x minus 3. And still in the denominator of x minus 3. You kind of notice that you can divide out this x minus 3 over x minus 3 because x is not equal to 3 in the domain. So we notice that we don't have to worry about it with the domain of this function. So now what you end up having, and maybe I should write this out because maybe you missed that, but just kind of keep in mind, it's okay to divide out since x is never equal to 3 in the domain of that rational function. That might be kind of useful to note so we remember. So if I'm finished with this expression, I have x approaching 3 the only thing I have left is x plus 3. When we look at this carefully, x plus 3 is actually nice, what we call it. So those linear functions. So now we are defined. I should say we are defined. The function is defined. And so if the function is defined at x equals 3, what you're allowed to do is you can do the direct substitution. You can plug in 3 for x. There was a 3 already in the expression. And now we get the actual value of the limit, which is 6. So I would like to point out, as I'm dealing with function notation and limit notation, whenever you simplify the arguments by means of factoring, rationalizing denominators, numerators, etc., you are not changing the fact that you're still trying to find the limit. So it's going to be very important that you always write out the limit notation until you actually use the direct substitution. That's when you're allowed to get rid of the limit notation. If you stop writing them, you're not making a clear statement. You're actually speaking false statements. So be careful on that. We'll kind of grade that when we look at the exam. So I want to warn you about that. So if we're kind of looking at this, maybe you weren't clear as to why we're allowed to divide out, or what's the issue with 3. You may want to look at on the side. So I'll kind of move over. They could ask yourself the question, how is y equals x squared minus 9 over x minus 3? How is that different from y equals x plus 3? So we can always use our TI to help us inspect this a little bit more. So I can plug in. If I'm using a rational function, let me clear the original part out. Usually I like to enclose the numerator in parentheses. Divided by the denominator, completely enclosed in parentheses, so we're not missing out anything. And I think I'm in a standard window. I'll press graph. And it appears that we have a line, but I would like to point out, if you actually try to figure out what's happening at x equals 3, if you press trace and you type in x equals 3, you will notice it does not give you a y value back. And that's because there's a hole there in the function. Or similarly, if you kind of look at the limits, you can kind of play with it, but be careful with that. If you were to type in y equals 3, or x plus 3, excuse me, graph it, it does look exactly the same. However, if you try to evaluate what's happening at x equals 3, you end up getting an actual y value. So rational function versus linear function, be careful. So I'll do a quick little sketch to help us out on that. So just a quick idea, with our TI, we noticed that when we graphed x squared minus 9 at x equals 3, there is a line, but at x equals 3, there was a hole there. Versus, same picture, but at x equals 3, it actually has a corresponding y value of 6. So be careful on that. A lot of times you can use your TI to inspect it. It's totally okay. So let's go back, go to our examples, go from there. All right, move this a little bit larger so we can see our writing. So now we are looking at evaluating a limit where the argument is a little more complicated than what we're used to. So before I start with my direct substitution, I want to see something really quick. So normally, the first inclination would be, can we plug in x equals -4 into this and be okay? So the first thing I kind of look at with rational functions is I really do look at the denominator and I say, if I were to try to plug in x equals -4, I'd have an issue. Notice it's not defined. So at this point, we do not want to plug this in yet. I'm hoping that I can try some algebra tricks. To see if I can simplify the argument down to something that I might be able to plug in x equals -4. And when I say algebra tricks, it's pretty much your prior math knowledge. We're looking at maybe, can we rationalize? Usually when there's radicals, that's kind of a key thing to try. Sometimes we can try to combine over common denominators. Sometimes we have two fractions. That might be another one to try. And we already tried the one above. We tried with factoring on example 3. But those tend to leave us in a good position to sometimes it allows us to play with the expression. So we can use actually direct substitution. So this is where I'm going on this one. If I'm going to use some math here, and I may need more space. Oh, excuse me, my left hand accidentally went to the other sections. I'm going to play with this. Let's see if we can. I'll rewrite it. X equals -4, or excuse me, x is approaching -4. So I'm writing the original function over again, just so you can see what I'm demonstrating. And a lot of times, because I see a radical and I cannot really simplify the radical or anything else, I think it might be a good idea to try to rationalize. And rationalize means, if you remember back, we're going to multiply by the conjugate of our numerator, because that's the one that had the radical in it. So I'm going to look at x squared plus 9 with the square root plus 5. That's the conjugate of x squared plus 9 minus 5. So whenever you multiply the numerator and denominator, they'd have to be by the same exact expression, so you're not really changing the value. So now if we were to do this, we're now going to have to bring back. Keep in mind, you're only manipulating the argument of the limit. You have not used any direct substitution or analytical ways to look at the graph. So we have not evaluated the limit yet. Therefore, we have to keep writing the words or letters limit as x approaches -4. So now we're going to run into a case where we're going to have to use some distribution or FOIL to help us out with the solutions to this or simplification of this argument. So I like to enclose the numerator and denominator in parentheses to help me remember that I'm actually multiplying binomial-like expressions. And play around with the multiplication. The numerators, if you were to multiply them out, they are a difference of square-like, so there are some shortcuts you can play with. We should get in the numerator the x squared plus 9, and then subtract off 25. If you were to go through distribution, combine like terms, you can do the same thing. Don't have to worry about the shortcut, but feel free to explore that on your own. It's the denominator that might take us a little time. There's no shortcut to it. So I use distribution. So see if I can dry this in orange, just so we can see this. The first terms, if I were to multiply that out, it's x times the square root of x squared plus 9. The second terms, that's x times 5 is 5x. First, outer, inner, last, remember that? Little FOIL there. So inner terms, 4 times the square root of x squared plus 9. And then the last terms, 4 times 5 gives me plus 20. So I have a very, very long expression in the denominator. So we can play and see what we have here. Okay, so let's play. Numerator for sure is a little nicer. I have limit as x approaches -4. And, very nice, x squared minus 16. Interesting. So if I see that, that's giving me kind of a clue, x squared minus 16, I'm interested. I could play with this, but I might be thinking, there might be something going on with, instead of me having to multiply out the denominator, I might be able to do this a little bit more of a shortcut. And actually I might. I don't want to waste your time, but I feel free if you want to explore this. It is possible if you were to plug in x equals -4 in the denominator at this point, you might end up getting something that ends up being nicer, but right away, this is what the interesting part is about calculus, is that sometimes you think to go a certain way and then you see something that pops up and I have another aha moment. So I'm going to change my mind because I'm allowed to. So maybe instead of multiplying out the denominator fully, and you'll see what I was seeing in a second, just by simplifying the numerator and noticing that I got x squared minus 16, it kind of gives me a hint. Maybe I shouldn't try to do any FOIL. Wasn't a bad review, wasn't it? Maybe I should really just say, let's just keep it the same. Let's keep it x plus 4 times square root of x squared plus 9 plus 5. Let's look at this. Now remember that difference of squares, very popular. Let's see if we can factor it out. And notice I keep having to write the limit because I have not evaluated the limit yet. X squared minus 16 is x plus 4x minus 4. And I'm really excited when I see this because you probably see it right now too. I have x squared plus 9 plus 5. Notice whenever you have factors, you can divide them out, and you're allowed to divide them out because the original function was never defined at x equals -4. So what you ended up doing for yourself, not infinity, excuse me, it is x is approaching -4. We are looking at x minus 4 over the square root of x squared plus 9 plus 5. Now, since we are defined at x equals -4, this is a good time to use the direct substitution. So if that is the case, we can now say we don't have to worry about writing the limit anymore because we're actually evaluating. We are looking at plugging in -4 wherever we see x, and seeing what happens when we simplify. So we should have negative 16 in the numerator. And if I was looking at the square root of 4 squared plus 9, that is the square root of 25. Actually, I don't want to run into my other example, so I'm going to go sideways, if you don't mind. I guess you have no choice. So let's look at, wait a second, negative 4 minus 4 is not negative 16. Negative 4 minus 4 is negative 8. But the square root of 4 squared plus 9, that's 16 plus 9 is 25. But then we also have a plus 5. Let me make that square root a little bit too large. Let's do this. Plus 5 is on the outside of the radicand. So that should leave me with negative 8 over 5 plus 5, which is 10. Negative 8 over 10. We can reduce it. We can leave it the same. We're in calculus. We have a little freedom. But WebAssign might want us to reduce. So I would say, what do we have? Common factors. Negative 8 over 10 gives us, let's see, 2 goes into 8 4 times. 2 goes into 10 5 times. So we might have this going on. So negative 4/5. Interesting. So you can play around. I'm kind of wondering, you know, if we were to plug in negative 4 to the denominator at this point, there might be something that allows us to plug it in and get the same result. But sometimes when you get stuck in your limits, you know, maybe the rationalizing worked. You may want to look for some certain shortcuts to see. And that's kind of what brought my attention back to, let's forget about, we can abandon our original process. We can see if we can factor out stuff and see if stuff divides out. So again, with this sort of problems, don't be afraid to experiment or retry them. That's the practice of all this calculus. Remember what we talked about. We're approaching it with a sense of not understanding the exact way to proceed until we see something better. So play around. We'll see how this goes. I'd like to also, I think you'll have a lot of chances to do this in WebAssign, so you can demonstrate your algebra that way too. So let's play with 2 more examples or so in this section, just to kind of give you an idea of all the different types of things we can see and everything we're pulling back from our past. So with example 5, we are looking at the limit as x approaches 0, and it looks like we have an absolute value over an x. I also noticed the denominator. If I were to try to use direct substitution, I'd run into some issues because that would make the function undefined. And I don't see any nice algebra tricks I can use when I'm dealing with this type of argument. So I have a little piece of advice. Anytime you see something strange, sometimes we call them weird, it might be a good idea, useful tip, to look at one-sided limits. If you ever see some of these strange functions where you really don't know how to proceed, a piecewise would be kind of an idea. For these types of weird functions. And I know we're not used to seeing the absolute value of x, but we did talk a little bit about, you know, some of the previous sections. We might want to recall that we did define the absolute value of x. If we were to play with it, you get 2 values. absolute value of x can be positive if, well, it always will be, if your x is greater than or equal to 0. It could be the opposite if your x is less than 0. So we're kind of talking about, you know, what's happening on the inside with this x if we're trying to solve for x. So this is a theorem that we're going to formalize from section 1.5, and we've already been kind of using it loosely, but they're trying to tell us that you can figure out your limits as long as your two-sided limits are equal. And we already figured this out with the matching. So it's just a formal statement from what we've already been playing with. So I want to point out that they're using another math notation right here. That is not a typo. IFF is mathematics for speaking if and only if. And a little bit of logic is saying that they are trying to talk about the left side versus the right side. So a little bit of proofing here, if you don't mind, a little sidebar. If the left side is true, that implies that the right side is true. So left implies right. And the if and only if part means it goes both ways. So also, if the right side is true, that implies that the left side is true. So a little bit of useful laterness, but we'll just apply it how we like as well. So what I would like to do is break this up into two pieces. I'm going to look at the left-hand side, and I'm going to look at the limit approaching from the left. So let's see if I can write this out. So the limit, I'm not going to use the generic notation, I'm using my actual example 5 notation. The limit as x approaches 0 from the negative side. So we're just rewriting this. And really this negative side and positive side is only going to affect what we're dealing with this absolute value of x. So just kind of make sure when you're going through this, if you're talking about approaching 0 from the left-hand side, I mean, you can even break this up in a quick number line if you'd like. Trying to find room for it on the page, but here, quick little number line, here's a 0. If you're speaking about numbers on the left of 0 and approaching 0, you're actually speaking about negative values of x. And that would indicate that your domain for that particular explanation is x is less than 0. So if we go back to our breaking up of our absolute value function into two pieces, it appears that we would be choosing to write negative x instead of the absolute value of x. We can redefine it based on the values that we're approaching. So I can write that in. I've got the limit as x approaches 0 from the negative side. Instead of writing absolute value of x, I'll write negative x. And now we get an expression that we can simplify the argument a little bit nicer. Remember, since we're not quite defined at 0, we can now divide out the values of x, x over x. And so you actually get the limit as x approaches 0 from the negative side of -1. And one of the properties of this section is if you're trying to take a limit of a constant, it doesn't matter what x is approaching, it's always going to be that same value. So we have -1 for the left-hand limit. Now we're going to just look at the other side. So I'm going to look at the right-hand limit. I'm just practicing my math with limit notation. Being careful, I'm always writing the limit because I have not evaluated it yet. I'm going to look at the limit as x approaches 0 from the positive side of our function, absolute value of x over x. And now kind of playing with that number line once again. If you're approaching 0 from the positive side, you're actually looking at positive values of x right here. And so that's telling us our domain is x is greater than 0. And if that is the case, we look at our definition of our absolute value into a piecewise function, we're going to be replacing x wherever we see absolute value of x. So now I can rewrite that right-hand limit, x approaches 0 from the positive side. Instead of absolute value of x, it's positive x. So now it kind of leads us to a little bit of simplification. X over x gives us a 1. And then by the same property, if you're taking a limit of a constant, you can actually evaluate it out and you get itself. Limit of a constant is itself. And so this is where we run into the question is, were the left-hand limit and the right-hand limits the same? Almost, but not quite. So we have ourselves different values. So what does that tell us? And I'll kind of summarize it mathematically. If you tried the limit as x approaches 0 from the negative side, you notice that it was not the same, not equal to the limit as x approaches 0 from the positive side. We would say the limit as x approaches 0 in general of this function does not exist. So all that work just to figure out that it doesn't exist. That's the beauty of calculus. But really, it allows us to utilize a lot of the properties we've been dealing with in algebra and really analyze what's going on with these functions without ever needing a graph. However, since we do have a nice TI in our possession, you might want to inspect the graph just to prove this for yourself. Or sometimes it does give you a heads up as to what the answer should be. So then you can also think backwards and use algebra to prove that as well. That's just a little helpful hint. So if I was looking at this, f of x equals absolute value of x over x, I can pull my TI up. It may or may not work, but I'm noticing that it's a piecewise function. Let's pull our TI up again. There we go. So now we have a little practice of entering absolute value of x. So that's done with the math key. And I'm going to scroll over to numbers, and that's the ABS. So I have my absolute value of x, and that's going to be divided by an x. I'm interested to see what shows up on the TI. And yeah, we got ourselves a piecewise function. Only thing with the TI is it doesn't always tell you what the endpoints are. So we'll go with the fact that it was never defined at x equals 0. So let me go back to our picture or our quick sketch. And it looks like the way we were dealing with this is that at, if it's not defined at x equals 0, there's a hole there, but there was a horizontal line. And the same thing here. I think is at 1 and -1, just so that we can see that. So you could very well see that if you're trying to approach 0 from the left-hand side, all of your y values are at -1. If you're trying to approach 0 from the right-hand side, all of your y values are at +1. So you can see right away you've got to jump. Therefore, the limit doesn't exist. So we can do this really quickly, but the proof behind it is what we're working on in calculus. So please remember that when you're working on your exams and quizzes. A little bit of one last thing. So we kind of progressively have gotten a little bit different functions as we go through the examples. I'll scroll through one more time. We kind of started off with some of the nice, straightforward, nice, smooth functions with example 1. With example 2, we're able to inspect the graph to help us out with the limits. Then we got a little bit more complicated with example 3. We had to use algebra as well as example 4. Anytime you have the radicals, the rationalization takes a while. And then we kind of run into, with example 5, some of those what we call strange or weird looking functions. And usually like a heads up, if you do see something like absolute value or a piecewise, splitting that up into 2 pieces, left-hand limit, right-hand limit is going to help you out on that. So there's a little strategy behind this. And finally, we're going to talk about what happens when you look at the particular limit you're supposed to work on and you can't really use any of the limit laws. Can't break this up into any of the techniques we've shown, examples 1 through 5. So we have one last thing that could save us if the limits are working. So I want to kind of draw this out for you so that you can see what I'm trying to describe. So what we like to say is with the squeeze theorem is we like to kind of figure out what's happening near a particular value. So let me see, I'm going to write in some nicer functions. So we have a function itself that maybe looks a little strange, hard for us to determine. Our job is to choose 2 functions that are relatively nice and we know their behavior. So we want to find 2 functions that we can squeeze our given function in between. And so that's what they're trying to say. If I can talk about this in plain English, they're asking us, hey, when f is stuck between g and h, near the particular value that we're trying to talk about. I'll draw an example. Sometimes concrete examples are going to help us out. So let's do G. I'll kind of make it look something like this. Nice function. It looks like part of it's a parabola. We'll see. And then we have H. We'll make it the same way in a way. So those are some nice functions that we can play with. But we're really interested in seeing what this function is. So a lot of times, it doesn't necessarily matter what's happening the entire part of f, but there are cases where you can inspect what's going on with the function. So it might not matter what's happening on the edges. It matters what's happening at that particular value or near that particular value of a. That's kind of our theme for the limits. So we're really interested in seeing what these values are approaching. And they're trying to say with the squeeze theorem, if you can squeeze the function in between 2 known functions at this point, then you can figure out where this limit is. Let me see if I can write that in there. You can kind of see it, but that's kind of our job. So I'd like to demonstrate this concrete example. We're going to look at, it looks like a periodic along with composition with, multiplication, x squared times cosine of 2 pi x. And this is where I run into like quick little note or caution. It's difficult for us to directly calculate using the limit laws. And another thing is in terms of when should I invoke the squeeze theorem? One of the hints I have for you is it's typically invoked when you have a bunch of sines or cosines. Some of those waves tend to help us. And the reason why we would invoke the squeeze theorem is when you have sines and cosines, sines and cosines are bounded. You guys remember the quick graphs, they're bounded by -1 and +1. So this is kind of the motivation behind why are we going to use this squeeze theorem. So if they're already bounded, that helps us out. So a little bit of a trick for you. I start off with the cosine part itself, or the sine, depending on what trig function we're looking at. So it could help us out if we play with just the trig function part. I'll write this in blue. So I have cosine of 2 pi x. And because I'm interested in talking about the fact that it's bounded, I remember that cosine is always in between -1 and +1. So this is kind of some facts I'm pulling from my trig class. Remember we talked about how we had to pull things randomly here and there, and now we have that application. And what you're trying to have to look at is you're trying to play with, well, how could I get x squared in consideration? So how do I make it look like x squared times cosine 2 pi x? And you can kind of see by the idea, if you multiply the inequality by x squared everywhere, you would say, what is it, x squared multiplied here, x squared multiplied here, x squared multiplied here. You're going to get -x squared less than or equal to x squared cosine 2 pi x less than or equal to +x squared. So what you've just done, you kind of utilize a little trick, is you kind of figured out what your two functions you're going to use for the squeeze theorem. Looks like we're going to play with f of x equals -x squared and f of x equals +x squared. And the trick, just so that we're kind of clear, I know I kind of showed you, is you are going to be multiplying the inequality by something. So once you figure out who the bounds are of your particular part of the function, cosine or sine, so you're multiplying the inequality by something, and sometimes we talk about number or function, that will not change the inequality. So we don't want to change the directions of the inequality. If you remember from algebra, the something, usually we're kind of referring to a number. Remember, you can't multiply an inequality by a negative number on both sides because it will reverse the direction of the symbols. And also, you can't multiply inequalities by 0 because things will disappear. So the reason why we were able to multiply all three parts by x squared is always greater than 0, greater than or equal to 0. We kind of don't care what happens at 0 because when we're looking at the original limit, oops, over here, notice that this is implying x approaching 0. We only care about what happens near 0. So this is the reason why we used x squared, and the fact that it kind of motivates it based on what we're seeing of what we want it to look like. And so that's kind of where I want to point out, and you're not allowed to multiply by 0, but we were looking at something where we're applying to be near zero. So be careful. Usually you'll kind of see the same sorts of things happening if you're asked to use the squeeze theorem, or if you're expected to apply it by just looking. So if we're actually looking at the squeeze theorem, and I kind of already demonstrated it here, when you find your two functions, and I'll actually use the TI to show you more in depth. If you look at what f of x equals x squared is, what f of x equals negative x squared, and you look at their behavior around zero, both of those limits, we kind of play with them. The limit of negative x squared. Oops, let me write that down, sorry. The limit of negative x squared as x approaches zero is actually still equal to zero. And at the same time, the limit of positive x squared as x approaches zero is also equal to zero. And since you're able to squeeze that function in between those two known functions with known limits by the squeeze theorem, your limit as x approaches zero of x squared cosine 2 pi x, the more complicated function, it also equals the same limit because it's squeezing between those. So that's a beautiful theorem. It's kind of allowing us to calculate limits without having to spend a lot of time with the computations. I can just demonstrate this with a TI before we leave, just so you see the pretty function. It always makes me happy when I graph these. So let's see. I'm going to graph the actual function we were talking about in example 6, the x squared. Let me try that one more time. X squared times cosine of 2 pi x. So that's the function in question. And then if we're actually typing in our two chosen functions, found by a little bit of thought, I wrote x squared, not x times 2. I'm zoomed in a little bit, but it's really pretty. Look at that, look at that. So again, you're really looking at, I'll take a screenshot because it's so pretty. I will take a screenshot and plug that into our lecture, just so you guys can see like the beauty behind this. I'm gonna paste this, hopefully. Oh, not on top of my page. Let's try this one more time. See if this will let me. One more time. Give me 1 second. We're gonna try one more time. Just like having it in my notes. And you can do this for yourself too. You can kind of play with this. There we go. It's just nice to have. So just so that we're clear on this, we had our two functions. We had the f of x equals x squared. And in our case, as far as the squeeze theorem is concerned, that was the h. And then the g part was the negative x squared. And so when we knew the limit of what's actually happening around x equals 0, in both cases, they are 0. So according to the squeeze theorem, that our function itself is approaching 0 as well. So just think about that. I will see you next section.